And now for the exciting conclusion to 20.6 notes, standard deviation, and variance. So this will be part B, and it will be the end, and it's also the conclusion of unit 20, I should say. So because populations are usually too large to gather data from every individual, a random sample must be taken, and the best we can do is just hope that it was a good representative of the population. So what can we do to try to ensure that we have a good representative sample? Well, we can ensure that the sample is sufficiently large. What does that mean? Well, to be honest with you, what is sufficiently large? I mean, there is no such thing as too much data, but most studies require 100 or more data points. So sample must be sufficiently large and taken in a way that is unbiased. We already talked about this, but you wouldn't go walk into a Starbucks and try to do a survey about people that like coffee because, well, let's be real, most of those people in there are going to like coffee. You know, they're not all in there for the pumpkin bread like me. So this table to the right, it shows us the notations that's used for samples and populations. Okay, so what we got? We've seen these the mean symbols, x bar and mu. And in the last lesson on variance and standard deviation, we saw Sn squared and Sn for variance and standard deviation of the sample. So for population, you have, this is little sigma. You know, capital sigma is the means summation, the big E thing. This is lowercase sigma squared. And again, square rooting is going to get you your standard deviation. Well, in general, the population mean mu and the standard deviation sigma, they just won't be known. So the population mean x bar, excuse me, population mean mu, and the standard deviation sigma will not be known. But we can use statistics from our sample to make inferences about the population. Now, when a sample of size n is used to draw inferences, draw conclusions about a population, the mean, x bar, of the sample is an unbiased estimate of mu. It's the best we can do. And S sub n, or standard deviation of our sample, is an estimate of sigma. It's the best we can do. So when data is grouped, meaning if all you have is a frequency chart and you don't have all the individual data points, then you can't just use the standard deviation formula that we were using before. We flip back to it so we can talk about it. This was the one that we used in the last lesson. See, we can't use this because this one requires you to know how far every term is from the mean. But if all you have is grouped data in a frequency table, you don't actually know all of the individual terms. So again, just like when we're finding the mean of that stuff, where we're having to use the mid-interval value and make the assumption that each interval is relatively normally distributed, you kind of have to make the same assumption when you're trying to find the standard deviation and the variance. So what we do is we say, okay, S sub n is equal to, it's still a square root. But if we have a frequency chart, what we could have is a product column. So what we'll do is we'll say add up the individual frequencies being multiplied to xi minus x bar squared, and then divide that by n. Here's the good news about these formulas. You don't have to have them memorized. Our calculators can do this stuff for us. So, I guess this one would require you to say xi minus x bar. So if it was grouped and you didn't know the xi's, then you would just have to use the mid-interval value again to see how far away it is from the mean, which you created by finding the mid-interval values anyway. But anyway, this just says figure out the distances from mean, square it, multiply it by the frequency, add those up, divide, square root, boom. But again, your calculator will do it for you. You don't even need to know this or understand that. Don't even worry about it. Basically, you just need to be able to see it and know when it's appropriate to use in case you need it for your IA. You never know. So remember, for continuous data or data that has been grouped in classes, we are going to use, like I already said, the midpoint or the mid-interval value to represent all the data in that interval. So we use the midpoint of the interval, also known as the mid-interval value. Use the midpoint of the interval to represent all data in that interval. Because that is often the best we can do. So much of statistics is the best we can do. It's not really an exact science, but whatever. I'm a mathematician, not a magician. All right, let's flip it over and do last couple examples of our unit. A random sample of 48 sheep was taken for a flock of over 2,000 sheep. The sample mean of their weights was 48.6 kg with a variance of 17.5. Okay, first we're going to find the standard deviation of the sample. Easy peasy lemon squeezy. Why? Because standard deviation of a sample, S sub n, is just the square root of the variance. That's why. And we know the variance, so that's just the square root of 17.5. Grab handy dandy calculator because yikes, square root of 17.5, and it is about 4.18 kg. I like this next part. So it says, hence, estimate the standard deviation of the population. Well, since standard deviation of a population is estimated by the standard deviation of the sample, we just say that sigma is also roughly 4.18. We don't have a choice. So sigma is approximately 4.18 since the sample is random. So it says find the unbalanced estimate of the mean weight of the sheep in the flock. Okay, once again, we use information from the sample to make estimations about the population. So since x bar equals 48.6, then we say mu is probably about 48.6. We don't have any other way of doing that. And then there was one. We've been tasked with finding the standard deviation of this distribution, and this is a grouped set of data. There's 5 possible scores. We knew there was 1 1, 2 2s, 4 3s, 2 4s, and 1 5. So we go, okay, well, time to start filling out some columns, some cells. Let's see, 1 plus 2 plus 4 plus 2 plus 1, that adds to 10. So this is a product column. It's the term times its frequency. Term times frequency. There. Now down here is going to be sigma fx, adding straight down. Gives us 30. This column requires us to know x bar. Oh, I guess we need to find x bar. Okay, fine. Let's find x bar. X bar is sigma fx divided by n, or 30 divided by 10. Our x bar is 3. So this column is going to be populated by these numbers minus 3. 1 minus 3, 2 minus 3, 3 minus 3, 4 minus 3, 5 minus 3. Summing these things doesn't mean anything to us, so I just went ahead and put a dash there, and also summing the squares doesn't mean anything either, so I put a dash there as well. But that's all this column is. This column is just this column squared. This way, again, we get positives only. 4, 1, 0, 1, 4. And then this last column, this is, once again, a product column. This column is the product of the frequency and this squared term. So 1 times 4, 2 times 1, 4 times 0, 2 times 1, and 1 times 4. Adding straight down gives us 12. Standard deviation is square root of sigma f x minus x bar squared over n. And this is 12. And n is still 10. And the square root of 12 over 10 is roughly 1.1. There you go. Now, I did tell you that your calculator can do all this for you. So I think it would be beneficial to know exactly how to do that, right? So let's go ahead and grab our favorite statistics tool, and let's ask the calculator to handle this stuff for us. So how do we do it? So we're going to be doing statistics now. That is what this stat button is for. So we press stat. And what we're going to do is we're going to edit some lists. So we're just going to enter on the edit. Boink. So we have L1, L2, yada, 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 on out for, I think I can go as far as I want. But what we need to do in L1 is put our scores in there. So 1, 2, 3, 4, 5. Then go to the right to fill out L2. L2 is going to be your frequencies. 1, 2, 4, 2, 1. 1, 2, 4, 2, 1. And you see I'm hitting down to get to the next term. Okay. We've now entered our data into our calculator. We're going to ask this calculator to perform some calculations for us. So we go back to stat, and we ask it to calculate some stuff. And this is a one variable statistic, meaning there was just a score. This is not a variable. This is just how many times that score happened. So there was a single variable, scores. So we highlight one variable statistics. So the first list was L1, but L2 was specifically a frequency list. So there's a very good chance that when you pressed enter on one variable statistics, this was just flat, this was just blank. This frequency list was blank. Because there's not always going to be a frequency list. So if there's not one, you just leave it blank and you go to calculate. But there is one this time, and it was L2 for us. So we do have to type L2. L2 is right there. It's a blue command, so you have to hit second before you hit the number 2. So second, the number 2, and then we just highlight calculate and hit enter. And it flashes in, ta-da! Look at that. It gave us X bar. It gave us sigma X. It gave us sigma X squared, which I don't even know what that's used for. I'm going to be real. It told you the N was 10, minimum was 1. It told you Q2, the median, Q4, the maximum, all kinds of great stuff. But we were specifically looking for standard deviation, weren't we? Here's SN, standard deviation of a sample, and here's sigma, standard deviation of a population. Our answer is 1.1 sigma x. In general, even if you are told that you are dealing with a sample in our class, you always use sigma x. And that is how you use your technology to help you do the mathematics. I hope you enjoyed.